Okay. So, apologies. Okay, good. Got the right file now. So what we're going to consider is a specific algorithm called the weighted majority algorithm. Okay, and it was sort of invented in the mid-90s. It's a way of comparing different policies. It's a way of summarizing expert advice whilst making a decision as to which advice to follow. Okay. So it's sort of sometimes thought of as kind of a meta-algorithm. It can be used in a variety of settings for comparing and making decisions. Okay. So what we're going to do is consider a policy that can achieve the lower bound that we discussed previously, this square root of t lower bound. Okay. This algorithm is sometimes called the weighted majority algorithm. Okay. And it's a parameterized policy, okay? So for a parameter eta, okay, the exponentially weighted majority algorithm is a randomized policy, and what you do is with each action, you associate a weight, okay? And then after each round of playing, you update the weight, depending on what reward you observe from each action. In particular, at the beginning, you set the weights equal to 1 for everything, okay? And then at the next round, you look at what reward you got from each action A, okay, given the outcome that just occurred, and then you take that to e to the eta, so you exponentiate it, and then you multiply it to the previous weight, okay? And then what I'm going to do is define W, capital W of t to be the sum of all the weights, okay? And then, it's really simple, then the action I choose at the next round, I choose with a probability proportional to the weights. Okay? Does that make sense? Alright? So each round, I just say e to the eta of the reward from the previous round. Okay, that gives my weight update. And then in the next round, I choose an action A with the probability proportional to the weights. Okay? And what you can prove is the following result for the weighting majority algorithm is that its regret, or its expected regret, okay, is eta to the minus 1 log of n. And remember, n is the number of arms that you have, okay? So if it's 100 arms, it's log of 100, okay? Plus eta t divided by 2, okay? And the one thing you can notice is if you're quite canny about the way you choose eta here, all right, then the expected regret of the weighted majority algorithm is 2 times square root of 2 times t, or square root of t, okay, so that's good, yeah, times log of n, all right? In fact, for this type of problem, that's just about as good as you can do, yeah? You can ever so slightly improve this constant here with this algorithm. The regret bound is square root of t, which is optimal, given what we previously stated. Also, its dependence on the number of arms is really good, okay? So one thing to remember is that logarithm, yeah, is an incredibly slowly increasing function, yeah? Like log of 100 is like 10, and then log of 13 is probably like, you know, a few thousand or whatever. You know, logs go, you know, they're about as slow as you can go to infinity as you like, okay? Remember that sum of 1 over n goes up like log, so you can think of adding a smaller amount each time, but it still goes up to infinity, okay? So look, that's great. So your dependence on the number of arms is really good. In fact, you can even show that's optimal as well, I think, in this case, okay? All right, so it's a pretty good algorithm for this type of problem, okay? A result that we're going to need in order to prove this is called Hofting's inequality, and one of your exercises in your homework will be to prove Hofting's inequality. It's not too hard, okay? So we need this bound called Hofting's inequality, which states for a bounded random variable that e to the eta of x is less than e to the eta of e of x plus eta squared divided by 2. Okay? It's just a bound. We can prove it. Take that for granted. Or we can do it in our homework. Okay? All right? Okay. And just to say with a kind of heads up to exams and all the rest of it, this style of proof is one that you can quite easily extend or manipulate and give slightly different algorithms and slightly different problems with, but the idea of the proof stays more or less the same. So study the proof maybe more than the algorithm if you want to do your homework in your exam and look at the past exam as well. Okay, so I think the proof is quite nice for this algorithm as well. So one is extremely robust for the problem setting that it is placed in. Also, it's quite a nice proof, and it generalizes under lots of little kind of perturbations, which I can ask a few exam questions. Okay, so yeah, right. Okay, so usually what we need is some sort of inequality for an upper bound, some sort of equality for a lower bound, and then we kind of use the same tricks in the middle. Okay, so let's do that. Okay, so we're going to go through bit by bit. So the first thing that it asks us is to show that w of t plus 1, okay, so this should really be a subscript, so just a small typo there. I probably should have written w of t plus 1 as a subscript. Okay, is equal to n times the product of the expected value of my policy, pi, at time t. Okay, and also that y of capital T should be little t, and it should be an omega. So that should be omega of t. It's a little typo there as well. Okay, all right. Anyway, so let's show that. So the idea is the following. So I can look at w of t plus 1, okay. I can think of it as a product. I can think of it as w is 0, and then I take the product from t equals 0 to t of w of t plus 1 divided by w of t. Okay? Okay. Does everyone agree with me that that's true? Because sort of like one term divides out the next term, and then we include it in the next one, and then they kind of cancel out. Okay? Yeah? All right. Now, let's think about what wt plus 1 is. So just think about that here. So w of t plus 1 is really the sum over all the actions of little w of t plus 1 of a. Yeah, because this capital W is just the sum of all the weights for each action. Okay? Agree with that? And then I can think about what that is. Well, that's really just e to the eta, the reward, okay, of the action action A, if I took it at the previous round, times wt of A. Okay, does everyone agree with that? So that's just the two definitions from previously. So that's just that definition and that definition. Okay? All right. So if I look at the bit that's inside this product here, okay, I'm going to get w is 0, product from t equals 0 to t, all right, e to the eta r a of wt. Oh, and I should leave a little bit of space for a sum, shouldn't I? Apologies. Sum over a. Okay. And if I'm being extremely mathematically rigorous, I should put some brackets in here. Okay. Wt of a divided by capital W. Does everyone agree with that? So I've just replaced that with this. Okay? All right? And Wt of A divided by Wt, what's that? If you can remember from before. Yeah, it's probability. It's the probability that the next round, okay, I choose A, around T that I choose A. Okay? So that is probability. That's the probability at time T I choose A. Okay? So that equality here. Yeah? So in other words, I've got a probability times some function. Probability choosing A times some function of A. Alright? In other words, I'm summing them up over all the A's. Okay? So really what I'm doing there is I'm just doing an expectation. Alright? Does that make sense? So that is equal to, and a final thing to note is that W0 is equal to N, because I said at the beginning I choose, or did I say W1? Maybe I should start at 1 here. I'm always bad at putting 1s and 0s in this, but anyway, okay, N. Okay? Yeah, it should be from 1. I'm being naughty. Sorry, 1, 1, 1, 1. Yeah, okay, now it's right. Okay, N product from T equals 1 to capital T of the expected value, okay, of E to the eta R of my policy, pi, at time T under the outcome that occurred. Okay? All right? So we've got something that's kind of vaguely moment-generating function-y. The next bit says, to prove that W of T plus 1 is less than or equal to N times the expected reward that I get under the weighted majority algorithm times eta plus eta squared times T. And I should have a divided by 2 in that eta as well. Typo again. Okay? Okay. So what shall I do to prove that? So let's put it another way. At what point did I write down eta squared divided by 2 previously? So you can look at this in another way. By process of elimination, I've used that inequality, I've used that equality, I've used that equality, I've used that equality. That's the statement of the thing we're trying to prove. So the only thing that's really left is that. Okay? So we're going to use Hofting's inequality. Okay? All right? So what does that mean? It means if I've got e to the x of a random variable, I can move the expectation upstairs. I can move it to the exponential. Okay? That's essentially what Hofting's doing for us here. Okay? So I can move that e up to the top, but the cost I have to incur is the eta squared divided by 2. Okay? So let's do that. So here, for each of these, I can apply Hofting's inequality, which essentially means I can move that expectation from outside the e to inside the exponential. Okay? So I'm going to apply Hofting. Okay. Move the expectation inside. So I'll write it like this. All right. N, the previous n from before. Then product T equals 1 to capital T. And I'll write it like this. Exp. Now I've been able to move the expectation inside here. Eta E of R of pi of T of omega T plus eta squared divided by 2. Okay? Okay. And then what I can do, well, I've got an exponential with a product outside, so I put it inside and make it a sum. Okay? So instead of producting up the expectation of these things, I'm actually summing up the rewards at each time from time t equals 1 to capital T. Okay? So some of the rewards. Okay. 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 I'm not sure, in your Martingale's course, do you get taught the Azuma-Hofting inequality? Okay. There's a Martingale version of this as well that's quite handy also. Do that later if you want as well, that's fine. Okay. Anyway. So that there is the sum of the rewards from time t equals 1 to t. So that's exactly this. It's the reward of the algorithm we're implementing, the weighted majority algorithm. Okay? All right. And actually, we've done quite a bit of the hard work now. So now we've got kind of an upper bound, okay, where the bit at the top of the upper bound is performance of our algorithm, okay. The next thing we're going to look for is a lower bound, where we compare it to the best action, okay. So that's what we're looking for here, okay. So we're looking for a lower bound that's sort of e to the e to something, where we're looking at the reward from the best action A or I, okay. So how might we show that? Well, one thing we can say is that we've got the sum, okay, of all the small weights at time t plus 1. Yeah, that's the definition of w of t plus 1. Okay. Well, the biggest of all these little WAs is certainly going to be in that sum, isn't it? Okay. So certainly we have the following inequality. Okay. Does that make sense? And then we can say, well, w of t plus 1 of A, well, let's just track back a bit. I'll just go back quickly. Notice little w of A, of action A, is really just the instantaneous reward from the last round, okay, times the previous one. So then, and then that one is just the instantaneous reward from the last round times the previous weight. We could just keep on going backwards. Yeah? Does that make sense? So if I kept iterating backwards, this would be just the same as... I don't have space. Wait. Zoom in really careful. This would be the same as... Oh, I need a smaller pen anyway. Exp r of t minus 1 times eta times exp r of eta t minus 2, and I could keep on going backwards, yeah? Does everyone agree with that? Okay? In other words, it's just the e to the sum of all the rewards. Okay? So really it's just equal to... You don't need to write this in your notes, it's okay. But, well, you can if you can write that small, but don't worry. Okay. All right. So in other words, I'll zoom out again. In other words, what I'm saying is that is really e to the eta of the sum of all the rewards from time t equals 1 to t r of a of omega of t. Okay? All right? And then that guy is really just the total reward of following action A at time t. All right? And then e to the eta, or the maximum I can just take inside because it's an increasing function. Okay? Assuming eta is positive, it's an increasing function, so I can also take the maximum inside. Okay? So, like, one of the things to mention is, like, when you first see that, it seems like you're chucking away a lot of information here, okay, by just considering the maximum instead of the sum of all the terms. But one way to think about it is if one term is really if one action is really beating all the others, okay, so its reward is a factor bigger than everyone else's, then e to that factor is going to be ginormous compared to the other terms, okay? So really the dominating term in this sum is going to be the best action, okay? And the other terms are going to be really small in comparison because the exponential is just going to inflate that. Okay? All right. Now we're kind of nearly done. Okay? So the next bit says to essentially prove the result. Okay? So I can basically get my answer from 122 and my answer from 121. Okay? So the answer here, okay, so by 122 and 121, okay, I'm going to have that exp eta, the maximum reward over all the rewards for following fixed action, is less than wt plus 1, which is less than, okay, the exponential of eta, the expected value of the reward from my policy, I'll just say pi rather than writing that weird symbol, okay, plus eta squared over 2t, and I'm forgetting an n at the front, okay? So that's 122, that inequality, and that's 121, that inequality. Okay, so I've got an upper bound that bounds against my policy and a lower bound that's to do with the best action. Okay, and now what we can do is take logs and rearrange. Okay, so if I take logs on this guy, that gets rid of that exponential and that gets rid of that exponential. I get a log n added on. Okay, taking logs, I'm going to get eta max of a of r of t of a is less than or equal to log of n plus eta e of r of t of pi plus eta squared over 2t. Okay? So I can take logs. Then I can divide by eta and rearrange a bit. Okay? So then I get max a r t of a minus the expected value of my policy okay, is less than or equal to, and divided by eta, so 1 over eta log of n plus eta, oops, no squared, sorry, divided by 2t. Okay? All right? And then that guy, by definition, is the regret of my policy. right. So next, let's do the last bit, which just basically says that I can choose a parameter eta such that I achieve this bound. Okay, and the answer to that's not too difficult. I just look at my upper bound and I minimize it over eta. Okay, so if I look to minimize the upper bound, I differentiate this guy. Okay, which is going to give me, well, minus 1 over eta squared log n plus t divided by 2 equals 0. Okay, that implies that eta is equal to t, oh sorry, let me get it right, log n, okay, that goes over there, and that goes over there, that goes over there, 2 over t, square rooted, yeah, I think that's right. Okay, and then I substitute this into this expression, okay, and I'm going to get 2 lots, okay, of this term. I might be a factor of 2 out here. I'm not sure if that 2 at the front needs to be there or not, but okay, anyway. Then substitute back in the expression. Okay. So just minimize this over eta essentially. Okay. All right, so good. So what are the main steps? Let's just, oh sorry, I'll let you finish writing down, sorry. Like I say, this is a proof you should try to learn off by heart for your exam or otherwise for life after finance at Manchester University. It is a useful meta algorithm. If you're doing some coding and stuff, it's a useful algorithm to have actually. Okay, anyway. So let's just recap the key steps of the proof. So the point was we needed an upper bound and we needed a lower bound. Okay. The upper bound, I had some clever inequality. It could be anything we like. Okay. In fact, we're going to do a similar proof in a minute where we're going to use a different upper bound. We're not going to use Hofting's inequality. Okay. Then we did this kind of clever interpolating product term. Okay. And from that, we kind of looked to find the probability that we were choosing the action at the next step. Okay, so we kind of did product, then we found an expression like this. Okay, then we applied our clever inequality. That gave us an upper bound in terms of the weights in terms of our policy. Okay. Then what did we do? We needed a lower bound, and the lower bound was to do with the best action that we could take. Okay. And we did something a bit more crude. We just said, well, this sum is less than the biggest term. Okay? So that was kind of like not too bad. And then we just put the two inequalities together and rearranged to see what we got. Okay? That's essentially it. Okay? So that's the basic structure. Interpolating product, clever upper bound, simple lower bound, put the two together, rearrange to see what you get. All right? That's it. Okay? All right. So you've been told. Okay. Right. So we're going to do that in a second for a slightly more sophisticated algorithm. I think, given the time, I'll give a description of what we're going to do tomorrow rather than go through all the proof. Okay. So we're going to start to kind of develop that algorithm because, like I say, it's one that you can extend and give different versions of. Okay. So there's a version of it for the multi-arm bandit problem. Okay. And So remember, and that a multi-arm bandit problem is a setting where if I try out a machine, okay, I don't know what would have happened if I did something else. Okay? So previously, if I pulled the arm on the machine, I got the results as if I'd pulled every single machine's arm, but I only got to keep the money from my own machine. Okay? So previously, it was almost like there's 10 machines, I choose my machine, and 9 other people try the other machines, and we see who got the most money. Okay? And I get to keep the money from my machine. In a multi-arm bandit situation, I just try the machine, I don't know what would have happened if I tried something else. Okay? Is that clear to everyone? Okay? So a bandit policy is a policy, pi of t, where our policy that we choose at time t is a function of the actions that the policy chose previously and the costs of those. Okay? I'm doing costs rather than rewards now. Okay? i.e., you cannot observe what would have happened if you'd chosen a different action. Okay? And what I'm going to define now is a policy called exponential explore exploit. Okay? So remember that when we're considering these multi-arm bandit problems, there's a trade-off between exploring all the different possibilities in order to learn about them and exploitation in the sense of trying to work with the one that's going to give you the most money or is going to cost you the least. Okay? All right. And so that policy is going to work as follows, is that for a parameter eta again, and costs, which we're going to assume are bounded between 0 and 1, the exp3, or exponential explore exploit, because notice it's quite a clever name, exp. Yeah, so people call it like x cubed. Yeah, okay, anyway. People with too much time on their hands, not me. X3 is a randomized policy which chooses an action according to sort of the previous rule earlier, okay, where we update the small weights as e to the eta of the cost from the previous round, but we're not going to work with exactly the cost that was observed because we're not always going to observe the cost. We can sort of replace it with what we think was going to happen if we tried that arm. Okay? So, and again, capital WT is the sum of all the weights. Okay? And again, we choose an arm or action A with a probability proportional to the weights. Okay? And here, the update that we do is we're only going to update the cost function for the arm that we tried, and we're going to divide it by the probability that we tried it. Okay? Now, the idea that we divide by this probability is because, well, with probability P of t, I'm going to try that arm, so the expected cost that we're going to get out of it, okay, is P of t times P of t, yeah, well, P of t times C divided by P of t, so you're just going to get the cost out again. Okay? There's sometimes an idea called importance sampling, so we kind of divide by the amount that we think is going to happen there, so it just kind of renormalize. Okay? And what we can show, and we'll show next time, is that the regret that we can get out of this policy, okay, is 1 over eta log n of t times eta divided by 2 t n. Okay, so the difference from the previous one is we didn't have this n here previously. Okay? In other words, if we choose the best eta that we could here, we're going to get something like 2 square root of 2 tn log n. Okay? So we don't get the nice scaling with the number of arms, but we still get the nice square root of t. Okay? So we still learn as well as the best expert. We're still sort of, you know, after 1 million trials or 1,000 out or something like that. But we do need to care about the number of arms that we have to try. Okay? And it sort of makes sense that there should be some dependence on n in this way because, well, you've got to try all of the arms in order to kind of discover which one's the best one. So you need to sort of constantly be trying them over time. And for that reason, you're always going to have this kind of n dependence. You can never get like a log n dependence. Okay? All right. So one thing I was going to show you, this isn't, I'll probably stop the video here at this point.